Right now, somewhere in your body, a banana you ate for breakfast is producing antimatter. No, really. About once every 75 minutes, a tiny piece of the universe's most expensive, most dangerous, and most mysterious substance is born inside you, lives for less than a billionth of a second, and vanishes in a flash of pure energy. So what exactly is this stuff? Why does it cost an estimated $62 trillion per gram? And why, by all the laws of physics, should we not even exist? Let's start with the basics. Everything you've ever touched, every star you've ever seen, every breath you've ever taken is made of matter. Matter is built from tiny particles like protons, neutrons, and electrons, and those particles have very specific properties. Electrons, for instance, carry a negative electrical charge. Protons carry a positive charge. That's just how the universe is wired, or so we thought. In the late 1920s, a quiet, almost painfully shy British physicist named Paul Dirac was trying to do something audacious. He wanted to combine Einstein's theory of relativity with the brand new field of quantum mechanics into a single equation that could describe how electrons behave at nearly the speed of light. And in 1928, he did it, but his equation came with a strange little surprise. Just like the simple equation x squared equals 4 has two answers, positive 2 and negative 2, Dirac's equation also has two solutions. One described the electron we all know and love. The other described something nobody had ever seen, a particle with the same mass as an electron, but with a positive charge instead of a negative one. Dirac could have dismissed it as a mathematical quirk. Instead, he made a bold leap. He suggested that this mirror-image particle must actually exist out there in the real world. And 4 years later, in 1932, a physicist named Carl Anderson was studying cosmic rays at Caltech when he found exactly what Dirac had predicted. He called it the positron, the anti-electron. Antimatter had gone from a strange mathematical solution to a measured, photographed reality. Both men later won Nobel Prizes for their work. Here's the wonderful, almost poetic thing about antimatter. Every single type of particle in the universe seems to have an antimatter twin. Electrons have positrons. Protons have antiprotons. Neutrons have antineutrons. The properties are nearly identical, same mass, same behavior, but the electric charge is flipped. If you could somehow build atoms out of antiparticles, with antiprotons in the nucleus and positrons swirling around them, you'd get anti-atoms. Anti-hydrogen, anti-helium, in principle, anti-anything. Scientists at CERN have actually done this. They first created anti-hydrogen back in 1995, and in 2023, they made an extraordinary measurement. They watched anti-hydrogen atoms fall and found that antimatter falls down, just like normal matter. Which sounds obvious, but until that experiment, nobody had ever directly confirmed it. Now, here's where things get dramatic. When matter and antimatter meet, they don't just collide. They annihilate. Both particles vanish completely, and all of their mass is converted into pure energy, usually in the form of high-energy light called gamma rays. This is Einstein's famous equation, E equals mc squared, taken to its absolute extreme. There is no more efficient way to release energy in the entire universe. To put that in perspective, if you could somehow combine just 1 gram of antimatter with 1 gram of matter, the energy released would be comparable to a nuclear bomb. Which is exactly why antimatter shows up in so much science fiction, from the warp engines of Star Trek to the thriller plots of Dan Brown. And it's also why containing antimatter is so absurdly difficult. The moment it touches a wall, a speck of dust, a single atom of normal air, it's gone. To hold on to it, physicists use ultra-high vacuums and powerful magnetic traps called Penning traps, which suspend charged antiparticles in midair using magnetic fields, so they never touch anything made of matter. You might be wondering if this stuff annihilates on contact. Where do we actually find it? The answer is surprising. Antimatter is everywhere, just in vanishingly small amounts. It pops out of certain types of radioactive decay, like the potassium-40 atoms in bananas. It rains down from space inside cosmic rays. And in 2011, NASA's Fermi Gamma Ray Space Telescope spotted something genuinely astonishing. Thunderstorms on Earth, ordinary thunderstorms, are launching beams of antimatter into space. The intense electric fields inside storm clouds accelerate electrons so violently that they create gamma rays. And those gamma rays convert into electron-positron pairs that shoot upward through the atmosphere. Scientists estimate that about 500 of these terrestrial gamma ray flashes happen worldwide every single day. Antimatter even has a practical job, one that saved millions of lives. If you've ever known someone who's had a PET scan, short for positron emission tomography, you've witnessed antimatter in action. Doctors inject a patient with a tiny amount of a radioactive sugar that emits positrons. Those positrons travel a fraction of a millimeter, meet electrons in the body, and annihilate, producing pairs of gamma rays that fly off in exactly opposite directions. Detectors surrounding the patient capture gamma rays and use them to build a three-dimensional map of where the sugar accumulated, which is incredibly useful for finding tumors, mapping brain activity, or diagnosing Alzheimer's disease in its earliest stages. Antimatter, the stuff of science fiction nightmares, is quietly working in hospitals every day. But here is the deepest mystery, the one that keeps physicists awake at night. According to our best theories, the Big Bang should have produced exactly equal amounts of matter and antimatter. They should have met, annihilated each other, and left behind a universe filled with nothing but radiation. No stars, no planets, no bananas, no you. And yet, here we are. The numbers suggest that for every billion matter-antimatter pairs that annihilated in the first fractions of a second after the Big Bang, one extra particle of matter survived. Just one in a billion. That tiny, unexplained surplus is everything we see in the night sky. Every galaxy, every nebula, every atom in your body is the leftover, the survivor of an unimaginable cosmic battle. Physicists call this puzzle the matter-antimatter asymmetry, and figuring out why it happened is one of the biggest unsolved problems in all of science. Experiments at CERN are right now comparing matter and antimatter atom by atom, hunting for the tiny difference that tilted the scales in our favor. So the next time you eat a banana, or watch a thunderstorm, or just look up at the stars, take a moment to appreciate something strange. The universe didn't have to exist. The math says it shouldn't, but somewhere in the first instant of creation, matter won by the slimmest possible margin. And that's why there's anything at all to wonder about. If this kind of cosmic detective story makes your brain light up the way it does mine, hit that subscribe button and let me know in the comments what you'd like us to explore next. Until then, keep looking up.